Organizations are constantly on the quest to secure their software, but in large systems it is both difficult and time-consuming to determine which parts are vulnerable. It is estimated that 1 hour of secure code review can cover only around 500 lines, but modern software applications are millions of lines long. This has led to great interest in automated software vulnerability detection techniques. Particularly, static application security testing, or SAST, is an attractive approach to help ensure software security early in development. In a recent large-scale study of open source software development, it was found that approximately half of the repositories use static analysis tools. Now, conventional tools for SAST typically operate through rule-based methods, leveraging knowledge from security domain experts. In this example, a tool uses its knowledge of buffer overflow vulnerabilities to create a check that automatically spots out-of-bounds buffer assignments. Whilst this is effective to a degree, there is a problem. These simple rules either produce a high number of false positive alerts or miss more complicated vulnerabilities. Hence, these tools actually struggle to make inroads in software development practices. From that same study of open source software development, 64% of the projects that used the static analysis tools only used them sporadically and didn't attach any actual consequences to their outputs. But now with the rise of AI and data-driven solutions, many difficult tasks are being automated with learning-based approaches. Static application security testing is no such exception. A model can learn from historical vulnerability examples to statically detect these patterns. Essentially, we can learn from our past mistakes. Data-driven solutions are rapidly growing in popularity due to the abundance of open source vulnerability data and continual technical advancements in AI. For example, Snyk, one of the top security vendors, has recently adopted an AI engine for their source code analysis tool. So, two methods of SAST have essentially emerged, but to date their use and analysis essentially exist in isolation. In this study, we determined the relative capabilities of these two methods, to what extent is SAST achievable, and what are the virtues of each method. Ultimately, what method should we look towards in the future? We have conducted our empirical study by analyzing the effectiveness of these approaches when applied on large open source code repositories. Now, to collect our data, we need two things: source code and examples of vulnerabilities in the source code. We collect 3 large open source repositories from the Linux kernel, OpenSSL, and Wireshark GitHub repositories, and then identify historical vulnerability examples in these codebases using records from the National Vulnerability Database. We selected these 3 repositories as they have many records and are very well documented in both NVD and GitHub. Additionally, to provide an alternative view of vulnerability examples, we also consider a vulnerability benchmarking dataset, the Juliet Test Suite. Unlike the former 3 datasets, this dataset contains synthetically created vulnerability examples. Next, we obtain our methods for analysis. For rule-based approaches, we collect a set of open-source rule-based SAST tools that have received widespread use in the community and by organizations. These are CPPCheck, ForFinder, and RATS. For learning-based approaches, we build SVP models using standard techniques that we observed in prior literature. These are 2 main types: models that make predictions from software metrics and models that make predictions directly from code tokens. We apply each of these tools to our collected datasets and measure their ability to provide warnings whether a file has a documented vulnerability example or not. Now, the most important capability of any SAST method is for it to actually be effective. For our first research question, we look into how capable each method is in actually detecting vulnerabilities documented in our dataset. For our second research question, on the other hand, we consider a secondary task after detection, which is vulnerability assessment. We look into how capable each method is at providing information about the vulnerability through classification of the vulnerability type. Can it provide us that extra information? Finally, given the similarity of the task that these two approaches are trying to achieve, we also investigate whether they can complement each other through combined use. For our third research question, rather than pitting each method head-to-head against each other, we investigate ways of combining their outputs to see if they can synergize through unity. These two graphs display the comparative performance of our rule-based SAS tools and our learning-based SVP models. We first noticed that the recall of these two approaches is not actually that different. Both approaches were able to identify a similar number of vulnerabilities, and when we compared the actual files that they were producing warnings for, we found quite a large overlap. They're able to predict similar things. However, when we look at precision, we notice that the SVP models drastically outperform the rule-based methods. This is because the SAS tools are producing a much larger number of warnings to inspect. They err on the side of caution, so they tend to over-warn and over-predict. This results in a very high number of false positives. When we actually manually inspected a sample of warnings from the SAS tools, we found the majority to be incidental. The warning messages were unrelated to the actual vulnerabilities. However, the SVP models we implemented operated as a black box, so we couldn't actually interpret the reasoning behind their outputs at all. They may also be incidental. For research question 2, we consider the capability of each method to predict the vulnerability type, whether they can provide us that extra information about the vulnerability. We again see that the learning-based SVP models exhibit a much better performance. But generally, the performance of both of these approaches is worse than that of the detection task from research question 1. This is because both methods are actually constrained quite heavily in the types that they can detect. The SAS tools can only predict the types that their rules and checks are built for and targeted towards. The SVP models similarly can only really predict types for which there's adequate training data. For the more obscure vulnerability classes, they were simply unable to predict them accurately because they weren't able to learn the patterns. Now finally, for research question 3, we investigate whether it would actually be better if we utilize both methods rather than pitting them against each other and picking one. We investigate two major approaches for their combination, which were inspired from previous attempts in literature. Firstly, we consider a naive approach in which we just use both methods in parallel and then combine their outputs. Now, this obviously produces much larger number of outputs, so consequently doing this is able to improve the recall, but it's had a significant degradation to the overall performance, so it's quite a negative result. Secondly, we see that predictive models can be enhanced by learning the knowledge produced by the SAS tools. Figure 4 displays in orange the performance improvement from the knowledge gained from the SAS outputs. The bars on the right display our best performing SVP model, which is created from the code tokens. However, in only one of the 4 datasets do we produce an output that is actually better than if we just use this SVP model on its own. Ultimately, the unification methods fall quite short as we are unable to really produce something greater than the sum of its parts. So in conclusion, we've provided a variety of insights to help vendors select appropriate approaches and SAS solutions, as well as the key pain points of both. Now, the two methods produce overall similar performance in terms of recall, but the SVP models produce several performance enhancements through high precision and better assessment. However, we note that the SVP models do exhibit several additional caveats. They need training data, tuning, and offer coarse granularity and interpretability. Hence, whilst learning-based approaches hold great promise for performance, they still have some additional barriers to adoption that should be investigated in future work. We look forward to promising advancements in this field.